then. So let's give it a shot. Okay. As I said, okay. I'm just missing Emmanuel. I wonder if he set his clock ahead. Okay. So it appears that we are recording, but whether I'll be able to upload it is another question. So let's move on from that. First, any questions from anything we've done so far? No. Okay. All right. Now, if I had this marked in the right place, it seems like we've done this. Maybe not. Okay. All right. This is in the middle of page 80. Is that about where you were? We did example 6. Okay. So just below example 6, if a row reduces, that's not a row, this is a capital A. If matrix A row reduces to an upper triangular matrix U, using only the row operation of adding a multiple of one row to another row below it, then A has a LU factorization. Okay? Now this has some ramifications, okay? But we'll get to that in a minute. And that upper echelon, goodness, why am I saying that? Upper triangular form, okay, upper triangular matrix is defined this way. If you had K elementary row operations, all of them being adding a multiple of one row to another row, remember, that's the case, and you did these all the way down to E2. Remember, you do them in reverse order. E1, A. Because you start with A and start doing these elementary matrices to it, which are elementary row operations, the matrices corresponding to that. And that gets you to an upper echelon, okay, upper triangular form, okay, upper triangular matrix form, okay. Now, A is then, if you take this form and multiply this by e to the k inverse, then of course you'd have to do this e to the k inverse, okay? And that goes to the identity matrix. So if you kept doing that over and over again, and then the next one you do e to the k minus 1 inverse, dot, 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 down to E2 inverse, E1 inverse, okay? Well, yeah, okay. That would leave you A, and that would be all these things, E1 inverse, E2 inverse, E3 inverse, dot, 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 all the way down to EK minus 1 inverse, times e to the k inverse, okay, times u, okay, that would be A. That would all be A then, if you did that to both sides. This combination here is then your lower triangular matrix, okay? So that's how we can get these. Now, there are sometimes easier ways, but, you know, possibly, but that's how we do this. Here, L is the product of the inverses of the elementary matrices used in row reduction, and you do them in reverse order, you know, or you can do them all together and it doesn't matter the order, okay? So once you have obtained an LU factorization of matrix A, you can then solve the system of n linear equations in n variables, ax plus b. That's our goal all along here. AX equal B. And you start by, and it says you can solve this very efficiently in 2 steps. Okay? I love the way they say that. Okay? Finding the U and then the L, that's long and hard. But once you got them, then it's very efficient to find this. And here's how you do it. You start by doing just U times X. Okay? And that's just going to give you some vector Y. Okay? And then do L onto Y, and L onto Y is LU onto X. Well, LU onto X is A, and this result here is your B. Okay? So let's see. Yeah. Now, so let's go back and say again, Y is equal to UX. That's pretty easy to do once you got the U. And then solve LY equal B for Y. Find out what the Y is, okay? Now, I thought you just did that. I mean, that's what the first thing is, except it's unknown Y in the first step here. And then when you actually solve it for Y, then the UX is equal to Y, okay? And solve that for X. So you solve the first one for Y, then you solve the next one for X, and then you have the column matrix X is now the solution of the original series because AX is equal to LUX, which is LY, which is B. Okay? Does it sound like to you you're going in circles? It feels like that to me too. When you actually do it, now they say the second step is simply back substitution because the upper matrix U, this one right here, okay, is upper triangular. So the first step is similar, except that it starts with the top of the matrix because L is lower triangle. For this reason, the first step is called forward substitution. Okay, a lot of blah, blah, blah. Let's actually do one. Okay? Here's your system. X1 minus 3x2 is equal to negative 5. X2 plus 3x3 is equal to negative 1. 2x1 minus 10x2 plus 2x3 is equal to negative 20. Now, I'm sorry? Yeah, minus 10x2. Yeah, that's 10. Okay, now, let's pause for a minute. Here's a system of equations. The good news here is that you have 1 as the upper, in the coefficient of the upper left. If this had been reversed, and this had been your top equation, and the others have been anywhere you wanted to put them, you could not use the LU method then, because remember, all you can use is multiplying one row by another, and you've got to get it in row echelon form. So, now this sounds bizarre. If you reorder your system before you start, then you can do that. If you have a 1 somewhere in that first column. If you don't, you can't do it with LU form. But if you have a 1 somewhere in the second column, like here, you could then rearrange your variables, okay, in the first equation. You'll have to keep up with this, and then be sure you start that way. So you have to set up your system so you have a 1 in the upper left. And once you've done that, you hope that you'll see this has a 1 here and a 1 there. It has the leading ones here. We hope that the techniques we'll use will carry you the rest of the way. Okay? Now, if you look at this matrix, the matrix you would get from there, okay? You tell me what it is. What would be your A here? Second? 1, -3, 0, 3, okay. Okay, there's your matrix A. Look across the page at example 6. That's your matrix A. So we don't have to go back and do upper, lower triangular. We don't have to do that anymore. We've got them already, okay? Now remember, it wasn't that hard to do, especially that upper triangular. You just row reduce, 2 steps and you're there. While you're doing that, mark down those inverse matrices and do them as well in the reverse order, and then you come up with your lower triangular, okay? So we've already done that, so we don't have to anymore. So let's write down what our U is. Well, they write it this way. I'm going to write it down here. The lower triangular is, lower triangular is 1, 0, 0. We did this last time. That's why I'm not redoing it. 0, 1, 0. And 2, -4, 1. Now notice you don't care what's in that lower triangular. There can be zeros there, but if they're not 0, it's fine. But what you've got to have so far is leading ones here and here. And so far, we've had ones in the diagonal. Is it absolutely necessary that be a 1 there? Probably not, but we don't know any reason not to. But we do have ones in the first 2 places, okay? And the reason I said probably not, look at the lower the upper triangular matrix that we had. 1, -3, 0. 0, 1, 3, and then 0, 0, 14. So you see there we don't have a 1 in the diagonal. So don't sweat that if we don't, but you really, so far it looks like you got to have them in those 2 places. Okay? But we already did that. That's done. All right. Now, what we're going to do now, if you go back to step 1, let y equal, this is a vector y, is equal to ux. Okay? Now, we haven't said what it is. We haven't done anything for it. We just say that's what y is, u times x. Okay? Now, we're going to solve the following system. Okay? And notice, all we did was say y is going to be this. We haven't figured out what it is yet. So the next step we're going to do is L, the lower y, is equal to b. Okay? Now the lower we're going to use. That's that first one. So that's going to be 1, 0, 2. I'm writing them downward this time. 0, 1, -4, 0, 0, 1. Okay? Multiply that by y1, y2, y3. We know it's got to be a 3 by 1. Okay? Okay? and then we'll set that equal to b, and our b was -5, -1, -20. Okay, done. All right. Solve this system using forward substitution. Start with the first equation, and that's pretty obvious, right? y1, 1 times y1 is equal to -5. Because you do y1 plus 0 plus 0, right? Is equal to -5. Right? Okay? So you say y1 is equal to -5. Got it. Okay? Now when you do the next one, still pretty easy. 0 plus y2 plus 0 is equal to -1. So y2 is equal to -1. Okay? And then the third one is this. 2y1 minus 4y2 plus y3 is equal to 20. That one we have to do something to. So 2y1 minus 4y2, are y'all following? Plus y3 is equal to -20. Got it? But we know what y1 is, -5. So that's going to be 2 times -5 minus 4 times -1 plus y3 is equal to -20. Well, this is -10 plus 4 plus y3 is equal to -20. Right? Well, let's add these two together. That gives you -6. So you add 6 to both sides, that gives you, I've run out of room, but I'll do it. Okay. You don't have room. Can y'all do that? Say again? -14. So y3 is equal to -14. Let's write it here. y3 is equal to -14. All right, done. Okay? Now, so there's your y vector. I need more room. Okay, what I think I'll do is go up here because we really don't need the a anymore, I don't think at all. So let's erase this because we're already done with a what we're planning to do with a. Okay? And let's go up top and continue with that. Okay? The last step then is x is equal to y. Okay? And we solve that for x. Okay? Well, the upper triangular matrix is this one. Let me write it here. 1, -3, 0, 0, 1, 3, 0, 0, 14. 14 looks suspicious, doesn't it? What's that? Okay. We did it last time. No, that was 14. This is from our example 6. No, this is upper triangular matrix. Here's L, this is U, right? That's what we're multiplying here. This is x1, x2. Huh? Yeah. U is this, okay? And this is equal to your y. And your y was -5, -1, -5, -1, -14. Pretty negative situation there, isn't it? Okay? Where do you think you're going to start here? At the bottom, exactly. Back substitution here. Let's not mess with that yet. Let's start here. To get this entry here, we do, that's the 3, 1 entry. You do 3 by 1. 0 plus 0 plus 14 x3 is equal to minus 14. What do you reckon that yields us? (14x3) is equal to minus 14. Solve for x3. Say again? A little louder? -1. Okay. So x3 is equal to -1. Okay? Now work our way up. This time we don't have a 0 there. We did in the last one, so it was pretty fortunate. See, that 0 helped us out a lot. We didn't need it, but we got it. So this is truly a back substitution. This is 0 minus x2, right? Minus x2 plus 3 times x3. 0 plus x2, so x2 plus 3x3 is equal to minus 1. Okay. Yeah, I still don't have room. So I think what I'll do, I need some room, so let's pick something to erase. We've already used this, so let's get rid of it. Okay. All right, let's write down what our last multiplication was doing. Row 2 times column 1. 0, x2, 1 times x2, plus 3 times x3 is equal to -1. But we know what x3 is, right? x2 plus 3 times -1 is equal to -1. That's x2 minus 3 is equal to -1. Add 3 to both sides, and you get x2. That's x2 is equal to 2. x2 equal 2. Right? All right. Now your top one. What does that give you? Do first row by the one column you got. x1 minus 3x2 plus 0. Thank you, 0. Okay. So that's x1 minus 3 x2 is equal to -5. Right? So x1 minus 3 times, what was x2? 2 is equal to -5. So x1 minus 6 is equal to -5. Add 6 to both sides, and you get x1 equal 1. You've solved the equation. Okay? Let's see if it works. 1 minus 3 times 2, that would be minus 6. 1 minus 6 is minus 5. That works. 2 plus minus 3 is minus 1. That works. 2 minus 20 plus, let's see, I'm lost here. 2 minus 20, that would be minus 18, minus 2 would be minus 1. Yeah. That's solved. Okay? So yeah, once you have the upper and lower triangular matrices, solve this one by forward substitution. You just make up this y here. Okay? Solve it by forward substitution. using the lower triangular matrix times some made up vector y, and put the b over there, and then with that operate on that from the right with the other triangular matrix, which you already had, and ux is equal to y, and when you do that, you wind up with your x.
So, was the y necessary, or?
What's that?
I said, was the y like necessary?
A y is an intermediate step to get you to the x's. You just sort of made it up, and if you're using this method, yes, it's necessary. You just have to figure out what that y is, and you see the reason is Lux is equal to b. If ux is equal to y, then L times y is equal to b. So you break your problem into two steps, and you do this one first and this one last, okay? Even though you started this way, and that's what they say. This is a step one. That's just identifying what your y is. Step two is then solving for y, and step three is then solving for x. So you start with this just to establish what y is, then you solve for y using that step, then you come back to this step and solve for x, and that gives you your answer.
So, like, if we didn't already have like the lower,
upper and lower?
yeah, so we'd have to find that first.
Okay. Yeah, and that's the long part. And in this problem, it wasn't too bad, if you remember. It wasn't too bad. But the question is why when you can do row reductions once and get your answer, okay? Here's why. Row reductions are not that easy to program. It's pretty easy to program. Good old CIS 250, right? 251, whatever it was. It's easy to program those, okay? You've already got matrix multiplication. All you have to do is now program it to come up with u and the x, u and the l. But remember, it's LU, Lulu, okay, not OO, okay. So, 1, 2, negative 1. That was our answer. And that finally finishes 2.4, okay? Homework exercises, as you've already been doing, hopefully. Any of the odds 1 through 7, either 9 or 11 or both, either 13 or 15 or both, either 17 or 19 or both. No, I'm sorry, any of the odds 17 to 21, either 23 or 25 or both, any of the odds 27 to 33. Trouble focusing my eyes. There's a true-false 3-part number 35. Not bad to look at that. Think through 37. Do 39. Do either 41 or 43 or both. Do 45. Think through 47. Now, here's one of these places that sort of aggravate me about this book. Okay, not bad, but just a little bit. In the homework exercises, they give you new concepts. Why don't they do that in the section and then maybe give you problems on it? Well, here's a new thing. It's called, and I don't even know how to pronounce it. It's a weird-looking word. Idempotent, idempotent. I don't know how you say it. Okay. Matrix. Determine whether the matrix is idempotent, or whatever that is. A square matrix A has to be square, is idempotent when A squared is equal to itself. Okay? So basically you square these two matrices and see if you get the same matrix. It has to be square, else you can't do it. So try either 49 or 51 or both. Okay? 53 then is a little more abstract. You come up with an A and a B such that it is idempotent, or however you say that. So do 53. Think through 55 and or, well, I'll say any of the odds 55 through 59, and that's it. The proofs are up to you. If you're a math major, do them. If you're not a math major but enjoy them, do them, okay? If you think it'll help you with this, do them, okay? So let's move on to example 2.5, okay? So let me erase all of this, and yeah. 2.5, applications of matrix operations. Now we're just going to do a couple of these and stop, okay? They're really fun. They're great things to do. That's why we do all this, but we really need to move on. Have any of you ever... let me think. I don't think I put any of these on the test. Okay? I don't think I did. Let me... Well, on the other hand, I haven't finished making up the test yet. No, I have. And I did not put any of them on it. But I did want to just go over them basically, because the first one, stochastic matrices. Have y'all seen or heard that word anywhere before, stochastic? You didn't take Chemistry 111. You didn't. They didn't use that term? Oh, you didn't. Okay. And a lot of times in chemistry, they talk about stochastic equations, and solving them stochastically, chemical equations. They may or may not have used it. Back when I took chemistry, they used the word a fair amount. Not a lot, but a little bit. So you see, you can use it in that case. P is called the matrix of transition probabilities, okay? And by the way, probabilities, if you didn't know this, the sum of all probabilities have to add to 1, because you can't have a probability of everything being any greater than 1, okay? That's what it's got to be. So basically, a matrix is a stochastic matrix when each entry in is a number between 0 and 1 inclusive. Notice, you can't have negative probabilities, you can't have probabilities greater than 1. So they have to be between 0 and 1 inclusive. That's what we mean by a stochastic matrix. If you're combining things chemically, the left-hand side, okay, all those things you're combining, you can't have more than 1, right? Yeah, because it's going to be some fraction of the total. Now, it could be there's nothing of this and 1 of this, so yeah, you can go with it then. So you see, that's what they're getting at. And that adds an application of that, not chemistry, is consumer preference, okay? What percentage of the people like this company over this company, or this company over that company? Well, they never can be more than 100%, right? So everything is a decimal number or a fractional number, something between 0 and 1. You don't have negative percents either, okay? You only have that. So consumer preference. Couple of examples there. The second example, applications of matrix operations. Are any of you into cryptology? You know what that is? Encoding, decoding. Okay, as in, what do they call it when you have a computer language, or you have a a thing that, yes, you've got codes in there, okay? I don't know if any of you watched, what's the name of that? I was just thinking of it before I asked the question. But in World War II, there was a huge project the British did to break the German code. And actually, they broke the German code before the end of the war. But they didn't advertise they broke the German code before the end of the war, because then Germany would have come up with a new code. So they had to, and this was really sad, they actually had to sacrifice situations, meaning people, ships, troops, because they couldn't let Germany suspect they had broken the code. And that was some tough decisions. I'm trying to think of what that series was called. But anyway, so if you're into encoding, and with cybersecurity nowadays, and making things secure, that's codes. Okay, so matrix operations are used for encoding and decoding. Okay, so I'll let you look at that. And just about every linear algebra text and most of your finite math text love this Leontief input-output model. Okay, and this is something that, say, industry and places like that use to come up with the most efficient system of doing things. This is a part of math and engineering they call, it's linear programming, but they have a name for it. And it's escaping me now. I just had it. This is a Monday, isn't it? I lost an hour's sleep. I don't know what it is. I just cannot think of the word. But they, optimization theory. Trying to optimize your input output. For the minimum input, what's the maximum output you can get? Optimization theory. Industrial engineers use this all the time. Whether they realize it or not, that's what their job is optimization. Okay? So there's Leontief. By the way, you could write on who in the world Leontief was. I would have guessed Russian. But the first paragraph's there. In 1936, American economist Vasily W. Leontief. If I've ever seen a Russian name, that's it. Okay? They probably pronounce it Vasily, but, published a model, and he received a Nobel Prize in economics for this work. Okay? People use it. It's powerful. It's a pain in the neck to teach. Okay? So I don't mind skipping it. But if you are interested in that, go for it. If you're going to be doing optimization in your engineering, if you project that, you might want to take a look at it. And by the way, I'll look at that first example there at the bottom of page, example 7 on page 90. That looks like a stochastic matrix to me, doesn't it? Everything is positive and less than 1. Okay? Between 0 and 1, inclusive. Okay? Then, and this is something I really wish we had time for, least squares regression analysis. Y'all know what that's talking about? Okay. In reality, when you're collecting data may look like that. Okay? You've got a trend there for sure. Okay? But how can you quantify that trend? What you try to do is get the best line fit for those data, or the best curve fit, or whatever. I did linear regression because that's what they're talking about here. Well, no, they're not. Okay? Least squares regression. Now, what do? Do you try to get the, okay, if that's a straight line, which it isn't, but let's imagine it was, And how far is this off the line? How far is that off the line? How far is that off the line? That one, if you measured all those and said, is that your best fit? Well, this would be plus, that would be plus, that would be a minus, plus, a minus, yeah. That's probably not your best fit, okay? But really, using plus and minuses, you can add to 0, and you say that's your best fit, but it's hard. Well, that's not how we usually do it, okay? Because you can't minimize, because if you moved it up a little bit, you'd have a negative. Well, minimize would be the biggest negative fit. So you don't want a negative fit. You want a 0 fit, but it's hard to get to 0. So here's what they do. Rather than take the absolute value of this, you square the difference, square the difference, square the difference, square. All are positive numbers now, right? Because squares are always positive. Plus squared is positive, plus squared is positive, minus squared is positive, plus squared, yeah. So you add all those together and minimize that. That's called the least squares fit. If you can minimize it, that's an easy thing, relatively, to get a computer to do is minimize, whereas finding the zeros sometimes is not quite so easy. So they do a least squares fit and minimize the 0. And it is done all the time. And that would be typically how you did that. Not eyeball it like I did. Probably came out wrong, okay? Least squares fit will get you there. So, and that's called least squares regression analysis. So, not responsible for anything in 2.5, but I wanted you to at least hear those terms in case you ever run into them again. If you keep the book, you can go back and see how to do it. Okay, what that means is we have finished Chapter 2, what we're going to cover in Chapter 2. And what I've got to do is find the test. Last week I did have a little bit of time one evening, and I made up your test 2. Okay, I think this is it. I sure hope it is anyway. Okay. Will any of you see the manual before I do? What's that? Yeah, I know. That's what I said. I'll see him in Cal 3. Okay. But, oh yeah, you didn't know he was in Cal 3. So I thought maybe if you had another classroom this morning, you could give it to him. Okay. If he's here for Cal 3, I'll give it to him then. Okay, let's move on to Chapter 3, which frankly I find probably one of the easiest chapters we're going to do. Boo hiss, y'all wanted the hard chapters, didn't you? Let's go with Chapter 3. Okay. And Chapter 3 is something that we have already touched on, determinants. Okay? What kind of matrices have determinants? Square. Okay? Remember, so many things we're doing now depend on being a square matrix. Okay? Every square matrix can be associated with a real number called its determinant. Historically, the use of determinants arose from the recognition that special patterns that occur in the solutions of systems of linear equations. All right, now this, I can't think of a worse way to introduce a chapter than this. But this is what they're doing, but hopefully it will give you the insight they hope it does, okay? If this was your system of equation, A11x1 plus A12x2 is equal to B1, right? A21x1 plus A22x2 22x2 is equal to B2. That's a typical two equation, two unknown, right? What would you do if you're needing to solve that? Go back to systems of equations. What would you do to solve that? Say again? Okay. You're going to do it that way. Okay. I said back when you were doing before, what did we do? The first thing you did was multiply the top equation by A21. No. The top equation by minus A21. I hesitate just because the signs will come out. I'm trying to do it the same way the book did. And the bottom equation by A11, right? Okay, now if these were numbers here, it'd make a lot of sense. But this is what you would do, right? So the top equation becomes A11 minus A21. I'm sorry. I don't know where the brain is today. Okay. Let me start over. Okay. All right. Minus A11, A21. X1 minus A12, A21, X2 is equal to minus B1, A21. Agreed? Okay. Let's do the second equation. That would be A11, A21, X1 plus A11, A22, X2 is equal to B2 times A11. Right? Yeah, I think I did it right. Okay. Now, what method do we call this? Remember back in solving linear equations, two unknowns, we call this elimination by addition. Remember? We would get these two so they had the same coefficient by multiplying whatever it took to get the same coefficients there. And notice here, these two add to 0, right? So that goes to 0. And then we have, I'll change the order, A11, A22 minus A12, A21 times X2 is equal to B2 A11 minus B1 A21, right? And then we solve this by dividing both sides by A11 A22 minus A12 A21 I can't write. Okay. A11, A22 minus A12, A21. Okay? That's what your X2 is. Now, if we had done the same type thing to X here, multiply the top equation by A22 and the bottom equation by minus A12, then we would have come up with an equation that looked a lot like this, but X1 would have been B1 go. They did it in the book. I'm not going to do it for you again, but it came up this way. x1 equals b1 a22 minus b2 a12 over a1 a22 minus a12 a21. Yeah. Well, they put them in reverse order, but it's okay. Now, notice what we've got. Notice what we've got. Both of these have a common denominator. A11, A22 minus A12, A21. Okay? The book wrote them minus A21, A12. It doesn't matter. Okay? Now, the other thing to notice are that these two things are the same in x2, and these two are the same in x1. Okay? Well, first, let's focus on that denominator. Okay? A11 times A22 minus A12 times A21. What does that look like? A11 times A22 minus A12 times A21. That's your determinant of a 2 by 2. And remember we said it can't be 0 for this to have some solution. Because if that's 0, undefined, undefined. There are no solutions if that's 0. If it's anything other than 0, yes, you have solutions. Okay? So, that's sort of the beginning of determinants. Okay? So, let's, strictly for a 2 by 2, and we've already done this, so this is nothing new. Here's the definition of a determinant for a 2 by 2 matrix. What we've already done before. Here's a matrix A, A11, A12, A21, A22. Sorry, those ones got sort of far apart there. The determinant of A and the single bars stand for determinant. Now that might look to you like absolute value. Don't get it confused with absolute value. You see single bars around a matrix, that doesn't mean absolute value, that means determinant. And you could also write it this way. A11, A12, A21, A22. Now it looks a lot like that, except there's no brackets there. Those are just single bars. And what is that? You've just given it to me. What would it be? A11, A22 minus A12, A21. Okay? The determinant of a matrix is a number. Okay? It's a number that's the products and sums or differences, usually differences are involved with it. Okay? So that is what we mean. The other way to express this is DET of A. Okay? And I hate writing DET. So I always put the bars. Okay? They're so much easier to write. Okay? And like you've seen, it's the product of the main diagonal minus the product of the off diagonal. Okay. For a 2 by 2. So let's do a few of these. They're really easy. We got 1 minute. Okay. Let's see if we can get at least one done. Well, it's fresh on your mind. 2, -3, 1, 2. What is its determinant? Second? Yep. 4. Say again? Plus 3 equal 7. Sure enough. We can't do it anymore. Sorry. I wish we'd have gotten started on time today. We could have gotten a little bit further. But I think you'll find, okay, now I'm probably preaching to the choir here, maybe not. Yeah, I think well, no, not quite, okay? You've already got your second test. Means I really need the first test in, okay? So please get me the first test. You've already got the second test. Let me just give you a heads up. Chapter 3 is, I think, only 4 sections, okay? And so it's one of the shortest chapters we'll have, and it's frankly a pretty easy section too, easy chapter. So it's not going to be much time before we finish with chapter 3. So please get your first test in and get working on the second one, because we're not going to be long before we got the third one on top of them. So keep them coming, folks. All right, good deal. We will see you all later today in various classes, Cal 3 or differential equations. Now,